So in this lecture, we are going to introduce the notion of orthogonality of plane waves. So remember when we discussed the Fourier series? So the Fourier series was a way of expressing a function on an interval. So suppose we had a function which was defined on an interval. So here we have the real line and we have some interval from minus L by 2 to plus L by 2, and we have some function, say f of x, that's defined on this real line. So the Fourier series was a way of expressing this function in terms of sines and cosines. But before we did that, what we had to do is that we had to extend this function over the real line, over the whole of the real line as a periodic function. So what we did is that we copied this function. So we copied the function and made it into a function which was periodic. And this new function, we gave it a different name. So we gave it the name, say, something like phi of x. And then we expressed this new periodic function as a linear combination, sines and cosines, which we can also write it in terms of exponentials. So if I'm given this function and I want to find the Fourier series, so this is the Fourier series. Then of course I would have to find what these coefficients are. In other words, I'd have to invert this expression. So to invert this expression, we used an orthogonality relationship, which is quite easy to prove. So we use the fact that if I integrate my basis functions over the interval, then I should get delta mn, where this is the Kronecker delta. This is of course quite easy to prove when m and n here are integers. So when m is equal to n, of course the argument is just 1. So the integrand, if we do the integration, then that just gives me L. So that L cancels with this 1 over L, and I get 1 as a result. If m is not equals to n, of course we can write this, the integrand, as sine and cosine function. And of course, because we are integrating the sine and the cosine function over one period, we should get 0. So that's one way to prove the fact that this is also 0 when m is not equals to n. So now the question is, what happens to this formula when we go from the Fourier series to the Fourier integral? So for the Fourier series, recall that the quote-unquote momentum modes are just these integers m and n, and they are discrete. But when we go to the Fourier transform, what we do is that we allow this period to go to infinity, and then we have a function which is defined over the whole real line. Of course, the function has to satisfy some conditions. Once it does that, then we can express that function as an integral. So this is something like so here, these AKs are the Fourier coefficients in the case of the Fourier transform. So this is the Fourier transform. So now for the Fourier transform, we should need some orthogonality conditions which are analogous to that. So if I now go to the limit where L goes to infinity, then the left-hand side is replaced by something like this, where now K1 and K2 are wave numbers whose values which take their value in the real line. So they are continuous variable. So because of the limit of this integral, we can see that this is not a convergent integral. If K1 is equals to K2, then of course this is not convergent. If K1 is not equals to K2, it is also not convergent because of these limits, because this is oscillatory, and these limits don't, they don't converge to any particular limit. So the idea is, how do we make sense of this formula, and how do we come up with an expression which is the analog of this expression in the limit where L goes to infinity? Now, why do we need to make sense of something like this? We have met in quantum mechanics the momentum mode, which was given by, say, psi of p of x. So this is a plane wave state, and it's given by e to the power I px over h bar. Now, if I'm going to find out what the Fourier transform of this is, then my Fourier transform formula is given by 2 pi h bar square root. I integrate this from minus infinity to plus infinity, and the argument is my function. And then, so I should use a different symbol here, because I'm using p over p prime, say. And here I have e to the power I p prime x over h bar d of x. Now, if I use the expression for psi p given here, then this integral becomes 2 pi h bar. Integral goes from minus infinity to plus infinity. And then I have here e to the power I, and over here I get e to the power, say, p plus p prime x over h, and then I have d of x. So to actually evaluate this thing, we need to evaluate this integral. This integral is exactly this integral, apart from a minus sign. Well, since we took the values of K1 and K2 to be real, that they can be either positive or negative, so this expression and this expression is exactly the same. So just for the sake of convention, we are going to take this sign to be minus, although if it's plus, it also works out. We have to figure out a value for this that is analogous to this. So let's look at the properties of the Kronecker delta. So what is a Kronecker delta doing? When the discrete momentum mode here, m is equals to n, it's 1. But when it's not equal to each other, this is 0. So therefore, we should demand that whenever whenever p is not equals to p prime, this should be 0. Okay, what are the other properties of Kronecker delta? So one of the nice properties of Kronecker delta is that suppose I am summing over all n, so n goes from say minus infinity to plus infinity, and I have the Kronecker delta, and I'm multiplying with it some quantity C of m. Then the summation of this is going to give me, C of n. So the summation of this is going to give me C of m. So in other words, whenever we have a Kronecker delta, and if you're summing over the index n, what the function that is multiplying this, only the value of that function where the index n is equal to m survives. Let me give this, this integral, which we don't know yet, a name. So let's call it delta. And let's give it it has two arguments, say p minus p prime. It should only depend on the difference between these two things. So then the analog of this expression should be that if I integrate, say from minus infinity to plus infinity, of this function dp minus p prime, and I multiply with this some arbitrary function f of p, and I'm integrating over all of p, then the value of f of p only when p is equal to p prime should survive this integral. So this should be equal to f of p prime. So clearly this expression is the continuum analog of this expression. So we have two properties of this function, which we're calling the delta function. One is this property. The other property is that delta is whenever its argument is non-zero, is 0. So if p is not equals to p prime. So this function is called the Dirac delta function. So this has a name. And it's not really a function per se. It is actually, in the mathematics literature, it's known as a distribution. So let's think about these properties a little bit. So what this is doing is that this function allows you to sample this test function f of p at a single value p prime. So this integral doesn't care what the value of fp is at values of its argument which is other than p prime. And this is what this is saying, that that function needs to be 0. But if that function, gives me, samples this function at a single point, this function needs to be a very peculiar type of function. In fact, you can show that this function then needs to be a singular function when its argument is 0. So when p is equal to p prime, the delta function is actually a singular function. It looks like a infinitely high spike, but in such a way that when you integrate it over some interval with some function f of p, it gives you the value of f of p. So let me give you an example of how to construct the Dirac delta function. So here is a representation of the Dirac delta function. So let me take delta x minus x prime. So this is going to be a function defined on the real line, which is x, and suppose there is a point on this function called x prime, then the delta function is going to be given by, so this is just one example, one way of constructing the Dirac delta function. There are other ways of constructing the Dirac delta function, which we will not go to in this video, but you can look it up later. So if I take a top hat function, so it's 0 everywhere, but around x equals to x prime, it just goes up and has a constant value. So this is going to be, this interval. I will take this interval to be a small positive number called epsilon. And then I will take this height to be 1 over epsilon. So this is the top hat function. Let me call this function let's call it, say, g epsilon of x. Then the Dirac delta function is given by g epsilon of x with the limit epsilon goes to 0. So this is a representation of the Dirac delta function. Let me try to convince you that this construction gives you this very important property. And so the way to do it is to actually, so we take a test function and we integrate this test function over all infinity. Now, this is going to be limit epsilon goes to 0. And now because, our top hat function is 0 everywhere except for an interval around x prime, so this integral just becomes an integral from x prime minus epsilon to x prime plus epsilon by 2. Sorry, there should be a 2. And then we have inside the value of this function is 1 over epsilon, and then we have our test function times d of x. Now if I take epsilon to be very small, and suppose our function f of x is a well-behaved function so that it doesn't wildly vary, then of course around this point x equals to x prime, it is going to be constant, and it's going to be constant, and its value is going to be f of x prime. In other words, we can write this as limit of epsilon goes to 0, and we can pull the function out, and our function is going to have the value x prime, at its value x prime. And in the interval, then we have x prime minus epsilon by 2, epsilon x prime plus epsilon by 2, and then I have delta e, and then I have delta x. Of course, this is the integral here is just going to give me epsilon, so therefore we are going to get from this thing just 1. As a result, we are going to get f of x prime. So we see that our our function, the Dirac delta function as we have represented here, does indeed satisfy this property. Of course, as we let epsilon go to 0, what happens to this function is that it gets thinner and thinner and taller. In the limit where epsilon goes to 0, it's a single point which is infinitely tall. So this is the this is the result. So let me just formally write this out. This is the expression that if I have a plane wave, so I have e to the power I, say px over h bar, and I have another plane wave e to the power I p prime x over h bar, and then their normalization is square root of 2 pi h bar, so multiplying two of those will give me just 2 pi h bar. And then if I integrate this, say over from minus infinity to plus infinity over d of x, then that is given by the Dirac delta function. And this is what we mean by the normalization of plane waves. So one last thing that I wanted to mention is that we can express this expression in terms of an inner product between two plane wave states. Then this would be given by in this way.